I'm going to do the derivation for Kepler's third law for the special case of a circular orbit. So first I'm going to start with centripetal force. The centripetal force an object feels when it's in orbit is the object's mass that is spinning, its velocity is tangential velocity squared, and its radius of orbit. Now, that's the same force that you feel because of gravity. So, and I'm going to make that mass number 2. So the gravitational force between an object in orbit is big G. The mass of the planet you're in orbit around, I'll make it mass 1. Mass number 2 will be the object in orbit, and it's the distance between you and the center of the object in which you are in orbit. So both of these give you the force that you feel when you're in a circular orbit. The centripetal force is caused by gravity, and we're looking at from the point of Newtonian gravity. I can set these two things equal to each other. So I have mass 2, velocity squared, your radius of orbit, big G, mass 1, the mass of the planet, mass 2, the object in orbit, and the distance between your centers squared. So mass 2 on both sides, we can get rid of it, I can get rid of that, and I get rid of that radius. So I end up with my speed is squared, big G. Now m, I'm going to go ahead and get rid of the subscript since there's only one mass left, but we need to remember that is the mass of the thing you are in orbit around. Now I'm going to do an aside here. I get an equation that will give me my orbital velocity. So if I just take the square root, orbital velocity is v, big G, the mass of the object in your orbit around, we have r, and I have the square root. So just as an aside, as I'm doing the derivation for the special case of Kepler's third law for a circular orbit, I get the equation that will give me the tangential velocity of an object that is in orbit. Now I'm going to go ahead and I'm going to put that square back, and I'm going to do some more substitutions. So you're traveling in a circular orbit. So the distance around, alright, let me just back up a little bit. So you're traveling in a circular orbit. Velocity is distance over time. Now, I can go ahead, how about I just do distance and the special case of time, which is period. How long it takes you to go around once and come back to where you started. Now, so the distance in which you travel when you travel in a circle is the circumference of a circle. And the circumference of a circle is 2 pi r. So I've replaced the d with 2 pi r. My time is still the special case. I'm using uppercase T because it is how long it takes for me to come back where I started from. So I'm going to go ahead, I'm going to distribute that square. I'm going to get 4 pi squared r squared t squared equals big G m, and I have an r. Now I'm going to go ahead, I'm going to move that r up, and I'm going to move the t up, the t squared up. So I have 4 pi squared r cubed big G m t squared. So in the next line, let's see if I can remember what that looks like. I'm going to keep the r cubed, and underneath that r cubed I am going to have big G. I'm going to have m, and the other side I'm going to go ahead and I'm going to put t squared, and underneath that I will have 4 pi squared. So that's one way that I can write, that should be r cubed right here. There we go. That's good enough cube. That is one way that I can write, let me see, get rid of that. It's one way that I can write Kepler's third law for a special case of a circular orbit.